I made little fairies out of paper. I folded them so I could pick up an ant without hurting it and carry it somewhere else. I put some sugar on a string I'd hung from the ceiling, completely isolated, so ants couldn't wander onto it by accident. I wanted control. I wanted to be a scientist about this. And I sat there, reading, watching, until an ant walked onto one of my paper fairies. Then I carried him to the sugar. Now, after a few ants had been ferried over, things started to get interesting. One of them walked back on its own and found the fairy. And I watched, very slowly at first, a message spreading through the colony. The rate of ants coming to the fairy started increasing, faster and faster, until I was going absolutely mad, ferrying ants back and forth. That's when it hit me. Something was going on that was more than just one ant figuring out where the food was. The information was spreading. The colony was learning. But here's the thing, and this is what I want to talk to you about today. No individual ant had the full picture. None of them knew what I knew. None of them had seen the whole setup. And yet, somehow, together, they were doing something that looked an awful lot like intelligence. So what is that? What do you call a kind of thinking that doesn't belong to any one thinker? I also found out, and this surprised me, that the ant trail isn't directional. If I picked up an ant that was walking along the trail, turned him around and around on a piece of paper, and put him back, he didn't know he was going the wrong way. He'd walk in the wrong direction until he bumped into another ant coming the other way. Then he'd figure it out. The knowledge wasn't in the ant. The knowledge was in the system. Now, I want you to hold that thought, because I'm going to come back to it. The knowledge was in the system. When a honeybee colony gets too big, they swarm. A large chunk of bees, maybe 10 or 15,000 of them, leaves the hive with the queen. They land somewhere, usually a tree branch, in a big vibrating cluster. And now they've got a problem. They need a new home. They need a place big enough, dry enough, high enough off the ground, with the right size entrance hole. There are very specific requirements. So what happens? Scout bees go out, flying in all directions. Each scout looks for potential nest sites. When a scout finds one, she comes back and dances. You've probably heard of the waggle dance. It's famous. The angle of the dance tells the other bees which direction to fly. The duration of the dance tells them how far. And here's the crucial part. The enthusiasm of the dance tells them how good the sight is. A really good sight, the scout dances for a long time. A mediocre sight, a shorter dance. Now, other bees watch these dances and go investigate the advertised sites themselves. If they also like a sight, they come back and also dance for it, adding their votes, if you want to think of it that way. Sites that are better get more dancers. Sites that are worse get fewer. The colony gradually reaches a consensus. But here's what's remarkable, and the biologist Thomas Seeley at Cornell has spent decades studying this. The swarm usually picks the best site, not just a decent site, the best one available. And it does this through a completely decentralized process where nobody is in charge. There's no scout who has seen all the candidates and is comparing them. There's no bee voting system with ballots. There are no committee meetings. Each bee just knows what she personally evaluated and dances for it. And yet out of all of this local, individual, piecemeal information, a globally correct answer emerges. Now, that is deeply interesting to me, because what it tells you is that you can build a smart system out of not very smart parts. You don't need a super intelligent bee. You just need enough bees communicating in the right way, following the right rules. And the smartness is a property of the collective, not of any individual member. That's what I mean by non-individual intelligence. The intelligence isn't in the bee. The intelligence is in the interaction. I think people don't quite appreciate how strange and deep this idea is. When we think about intelligence, human intelligence, our kind, we tend to think of it as something that lives inside a single brain. You have a brain, it thinks, it decides, it solves problems. The brain is the locus of intelligence. But wait a minute, what is a brain? A brain is about 86 billion neurons. Each neuron is a cell. It fires or it doesn't fire. It sends a little electrochemical signal down a wire and talks to other neurons. Each neuron, by itself, is not intelligent. It can't do arithmetic. It doesn't have opinions. It can't feel wonder or curiosity. It just fires or doesn't fire. And yet you, the collection of 86 billion of these firing and not firing cells, can do all of those things. You can read, write, compose music, fall in love, prove theorems, get embarrassed at parties. lie to yourself, and feel inexplicable sadness on Sunday afternoons. Hell, how does that happen? How do you get feeling and thinking from firing and not firing? I don't know the full answer to that. Nobody does. It's one of the genuinely deep mysteries. But here's what I do know. The principle is the same as the ant colony. The principle is the same as the bee swarm. Intelligence and complex behavior can emerge from the collective activity of many simple units, none of which individually possesses that intelligence or complex behavior. This is what scientists today call emergent behavior, and it's one of the most profound ideas in all of science. The whole can be qualitatively different from the parts, not just bigger, different in kind. The ants can find the shortest path between the nest and the food. Individual ants cannot. The bees can identify the best available nest site in a large geographic area. Individual bees cannot. Your brain can experience the color red and feel the weight of regret. Individual neurons cannot. The thing you want to understand is doing something that none of its parts can do. That's not magic. It's emergence. But it is, I have to say, genuinely marvelous. Now, I want to explain the pheromone trail thing more carefully, because it's a beautiful example of how you can get sophisticated collective behavior from very simple individual rules. An ant walks out of the nest, foraging. She walks kind of randomly. Eventually, she finds food. Now she picks up a piece and walks back to the nest. And as she does, she lays down a chemical, a pheromone, on the ground behind her. It evaporates over time. The trail fades. Now, other ants come out. They can smell this trail. They tend to follow it. And if they go to the food and come back successfully, they also lay down pheromone on the same trail, reinforcing it. Meanwhile, a longer path, one that some other ant has blazed, takes more time to walk. So by the time the ant gets back, some of its pheromone has already evaporated. The shorter path gets reinforced faster. And over time, as more and more ants choose the stronger smelling trail, which is the shorter one, the colony converges on the most efficient route. The individual ant does not know that she's optimizing a path. She doesn't have a map. She doesn't solve an equation. She just follows the smell and lays a little more smell. And yet the colony finds something that mathematicians call a geodesic, the shortest path between 2 points. The computer scientists have noticed this, by the way. They've built algorithms inspired by exactly this process. They call them ant colony optimization algorithms, and they use them to solve some very hard problems, like how to route traffic through a network, or how a salesman can visit a large number of cities in the shortest total distance. These are problems that are computationally very hard to solve exactly, but ant-inspired algorithms can solve them approximately, and quite well. So we've taken an idea from ants and put it into computers, and it works. Because the underlying principle, reinforcement through collective action, convergence through iteration, is genuinely clever. We just discovered it in ants first. Let me tell you about army ants. Because army ants take this collective thing to a whole other level that I find almost frightening in how impressive it is. Army ants don't have a permanent nest. They are a nomadic society. The colony, which can contain hundreds of thousands or even millions of individuals, moves through the jungle in massive raiding swarms, consuming nearly everything in their path. Insects, spiders, small vertebrates. The swarm can be 30 meters wide. Now, how do you coordinate that many animals simultaneously, in the dark, in complex terrain, with no leader, no plan, no map? The answer is, they build their infrastructure from their own bodies. Army ants build living bridges. When the column needs to cross a gap, a crack in a log, a space between leaves, workers gather at the gap and lock themselves together with their legs and mandibles, and other ants walk over them. The bridge is made of ants, and the bridge is adaptive. If the traffic increases, more workers add themselves to make it wider. If the traffic drops, workers at the end slowly detach themselves and rejoin the column. The bridge grows and shrinks in real time in response to need, with no one giving orders. They also build living rafts. When army ants encounter water, a flood, a stream, they do not drown and they do not stop. They form a raft out of their own bodies, with the brood, the larvae and pupae, in the middle for protection. The raft floats. Ants on the bottom, submerged, hold the raft together and use their bodies as air pockets. They paddle. The colony crosses the water. Then the raft disassembles itself. Now, I want you to think about what you would need to engineer something like that. A self-assembling, self-disassembling, load-bearing, adaptive structure made of individuals that reconfigure in response to real-time conditions with no central controller. That's an enormous engineering challenge. We struggle to build robots that can do remotely analogous things, and we're using computers and sensors and actuators. The ants do it with pheromones and touch, and a few thousand neurons per individual. There's something here that should make you humble. We have a tendency, and I think it's understandable, but it's still a mistake, to equate intelligence with the kind of intelligence we have. Big brain, centralized, deliberate, symbolic, language and logic and planning. And we look at an ant and we say, well, that's not very smart. It's got what, 500,000 neurons? We've got 86 billion. But that framing is wrong. Intelligence is a relationship between a system and its environment. The question is not how big is the brain. The question is, can the system solve the problems it faces? And by that measure, by the measure of does it work, the ant colony is doing something extraordinary. Here's a question I want to put to you. When we say the ant colony is intelligent, what exactly do we mean? Where does the intelligence live? Not in any individual ant. We've established that. Pick up one ant, isolate it, and it's helpless. It can't build a nest. It can't find optimal foraging routes. It can't form a bridge or a raft. It wanders around and eventually dies. The intelligence lives in the collective. But the collective is just ants plus communication. Ants and their chemical signals, their touch, their behaviors triggered by those signals. So you might say, the intelligence is in the interaction. It's the pattern of information flow between individuals that gives rise to intelligent behavior. Not any single message, any single pheromone molecule is meaningless, but the statistical pattern across millions of signals, across thousands of individuals over time. This is related to something I think about in physics. In physics, we have a concept called entropy. In a gas, say, in this room right now, the air, there are something like 10 to the 27th molecules, an incomprehensible number, flying around and bouncing off each other. Any individual molecule doesn't have a temperature. Temperature is a property of the collection. Any individual molecule doesn't have a pressure. Pressure is a property of the collection. These macroscopic properties we can measure: temperature, pressure, density. They emerge from the statistical behavior of the molecules. The individual molecule doesn't have them. The collection does. Something analogous is going on with the ant colony. Decision-making is a property of the colony. Problem-solving is a property of the colony. These aren't properties of any individual ant. They emerge from the statistical, collective behavior of the ants interacting with each other and with their environment. So in a sense, the colony thinks. Not metaphorically, not it's as if the colony thinks. The colony actually performs computations, integrates information, and produces adaptive responses to its environment. That's what thinking is, when you strip away all the poetry and get down to what's actually happening mechanically. Now I want to talk about a subtlety here that I think is really important and often gets missed. The collective is not always smarter than the individual. That would be too simple. The relationship between individual and collective intelligence is more complicated and more interesting than that. There's a beautiful experiment with temnothorax ants. Those are small ants that live in rock crevices. Researchers gave the ants a choice between two potential nest sites, one better than the other, and varied how different the two sites were. When the difference between the good site and the bad site was large, when it was easy to tell them apart, individual ants were actually better at picking the right one than the colony was. But when the difference was subtle, when you needed to be really discriminating, the colony outperformed individuals. And this makes a certain sense when you think about it. When the right answer is obvious, deliberation just slows you down. If one nest site is obviously great and one is obviously terrible, you don't need to run a whole collective decision-making process. Just pick the good one. But when the signals are ambiguous, when you need to integrate subtle information, that's when aggregating judgments across many individuals starts to pay off. This is true in other contexts too. There's a principle in statistics. You might know it as the law of large numbers. That says if you take a lot of noisy, independent measurements of some quantity and you average them, you get a much better estimate than any single measurement. The noise averages out. The signal survives. The wisdom of crowds, people call it. the idea that the collective judgment can be more accurate than any individual's judgment. But, and this is important, this only works if the individual judgments are somewhat independent. If everyone in the crowd is thinking the same way, copying the same source, influenced by the same bias, then you don't get the benefit. You just amplify the error. A herd moving in the wrong direction is still moving in the wrong direction and moving faster. With ants, the individual assessments are independent in the right way. Different scouts explore different territories. They bring back genuinely different information. The communication process aggregates those independent assessments. That's why it works. I want to make a connection now that I find genuinely exciting, which is to the question of what intelligence actually is. There's a traditional view, and I think it comes partly from religion and partly just from being human, that intelligence is a special property of certain special things. It lives in minds. Minds belong to persons. Persons are special. But the picture that emerges from biology, from studying ants and bees and slime molds, yes, I said slime molds, hold on, is that intelligence is much more widely distributed than that. Intelligence, in the sense of adaptive information processing, of solving problems, of responding appropriately to a complex environment, is something that emerges wherever you have the right kind of organized communicating system. Now the slime mold, Physarum polycephalum. This is a single-celled organism, but it can grow large, spreading out across surfaces like a yellowish network. And here's the thing, it can solve mazes. Researchers in Japan put slime mold in a maze. They put food at the start and the end. The slime mold, seeking nutrients, extended itself through the maze, filling all the passages. Then gradually, it retracted from the dead ends and non-optimal paths until what remained was the shortest route through the maze. One cell, no neurons, no brain, solving a maze. There's an even better version of this experiment. The researchers recreated the geography of the greater Tokyo area on an agar plate. They put food sources at the positions of major cities. They let the slime mold grow and optimize. And after a while, the network of tubes that the slime mold had built to connect the food sources looked remarkably like the Tokyo rail network, the actual rail network that Japanese engineers had spent decades designing and optimizing. Now why? Why would a slime mold build the same network that professional human engineers built? Because the problem both were solving is the same problem. Connect these nodes efficiently, with redundancy in case one path fails, minimizing total material while minimizing maximum travel time. That's the problem. And good solutions to that problem look a certain way, regardless of whether you're a slime mold, an ant colony, or a team of engineers. The intelligence, if you want to call it that, is in the structure of the problem. Any system that gets around to actually solving the problem, well, will converge on something like the same answer. This is, I think, a deep point about the nature of intelligence. It is not an ethereal quality. It is not a spiritual gift. It is the capacity of a physical system to find good solutions to problems. And there are many ways, many very different physical systems that can do that. I want to come back to the human brain now and put what we've been talking about in a new light. Your brain is a colony. It's not a single thing that thinks. It's a vast cooperative of cells communicating through chemical signals and electrical pulses with different groups of neurons specialized for different functions, with no single seat of control, with emergent behavior arising from distributed interactions. There is no you sitting inside your brain, looking at the sensory information coming in, making decisions, sending out commands. That feels like what's happening, but it's not what's happening. What's happening is very much more like the ant colony. Different regions of your brain are processing different aspects of your environment simultaneously, independently, and in parallel. They're communicating, competing, cooperating. A decision emerges from this distributed process, like the bee swarm reaching consensus on a nest site. And then it becomes your conscious experience of having decided. But the decision wasn't made by you in the sense of a homunculus, a little person inside, sitting at the controls. It was made by the colony of neurons through their collective dynamics. You are the bee swarm. You are the ant colony. You are, in a very real sense, a hive mind. I find that simultaneously disturbing and wonderful. Disturbing because it undermines a certain picture of selfhood that we find comforting. Wonderful because it connects us, deeply connects us, to those ants on my Princeton windowsill. We're doing the same thing, with different implementation. Let me tell you about one more thing, because it's so strange and so beautiful that I can't leave it out. Division of labor in ant colonies. A colony of leafcutter ants, say, in the tropical forest. These are the ants you see carrying little pieces of leaf above their heads, looking almost comical, like tiny umbrellas. They're not eating the leaves. They're farming. They take the leaves back to the nest, chew them up, and grow a fungus on them, which they eat. They're fungus farmers. Now, in this colony, different ants specialize in different tasks. The major workers, large ants with big heads and mandibles, do the cutting and carrying. The minor workers clean the leaf fragments and tend the fungus. The minims, the smallest ants, do the most delicate tasks, tending the larvae, managing the fungal garden. And the remarkable thing is that this division of labor is not assigned by anyone. There is no foreman who looks at a newly emerged adult and says, "You're going to be a cutter." The ant figures out its role through a process of interaction with the colony, with the tasks that need doing, with the responses she gets from nestmates, with the chemical signals in the environment. The colony self-organizes its own workforce in real time. As needs change, as workers die, as seasons change what's available, the workforce composition adjusts. If you remove all the majors from a colony, the minors don't just fail, they begin to grow slightly larger, and some begin taking on the cutting tasks. The colony compensates. It responds to perturbation. How does it do this without anyone telling it to? The answer is feedback loops. Each ant responds to local conditions. If there are not enough ants of a certain type doing a certain task, signals accumulate. Things don't get done. Certain chemicals build up or run low, and other ants respond to those signals by changing their behavior. No individual sees the global picture, but each individual responds to local signals that encode information about the global state. It is, in a very real sense, a form of computation. The colony is computing what it needs and dynamically allocating resources to meet those needs through a completely distributed process. So where does all of this leave us? What should we take away? I think the first thing is a sense of wonder. Genuine wonder. Not the kind where you say, "Wow, that's neat," and move on, but the kind that sits with you and changes how you see things. Because if you really absorb what the ant colony and the bee swarm are doing, if you really appreciate that a brainless system can find optimal solutions, build adaptive structures, run a farming operation, and make collective decisions, if you really get that, then the world looks different. Intelligence is not as rare or as special as we thought. It is what happens when systems are organized in certain ways, when information flows in certain patterns, when feedback is structured correctly. It can happen in neurons, yes, but it can also happen in insects, in slime molds, in cells, maybe in other things we haven't appreciated yet. The second thing I take away is an insight about what makes collective intelligence work. It's not just having a lot of agents. It's having agents that are somewhat independent, so they bring genuinely different information, and having a communication process that aggregates that information without just amplifying noise. The bees only work because different scouts evaluate different sites. If they all went to the same site and danced the same dance, you'd get a mob, not wisdom. And the third thing, and this is the one that I think has the most personal relevance, is a reconsideration of what we mean by I. When I say I thought of something, or I decided to do X, what is this I? It turns out it's a colony. It's a collective. It's a hive. The thought didn't arise from some unified, indivisible self. It arose from the collective dynamics of billions of neurons, shaped by genetics, by experience, by the particular pattern of inputs you received this morning. The I is the swarm's experience of itself. Now, maybe that's troubling to some people. Maybe it feels like it takes something away, but I don't see it that way. To me, it makes the whole thing more interesting, more mysterious, and it gives you a strange kind of company, knowing that the process that gives rise to your sense of self is not so different in its fundamental logic from what's going on in that ant colony. The ants don't know they're intelligent. The colony doesn't have a sense of itself, and yet it is, by any functional measure, doing something that deserves the word smart. And you are a colony that has become aware of itself. You are a hive mind that can ask the question, what is a hive mind? I think that's worth sitting with for a while. Now, before I go, there's one more thing from my Princeton days with the ants. I noticed that the ant trails look remarkably straight, almost geometric. And I figured the ants must have some kind of sense of geometry, some way of knowing to go in a straight line. So I did experiments to test this. I tried to see if I could demonstrate their geometric sense. The experiments didn't work. The trails weren't straight because individual ants were navigating geometrically. The trails became straight gradually, through the same pheromone reinforcement process. Short deviations got reinforced, long deviations got abandoned. Over time, the trail straightened out. What looked like individual geometric intelligence was actually collective optimization through iteration. I tried to make the ants go around in a circle. I thought if I could create a closed loop, they'd walk around forever, reinforcing each other. But I didn't have the patience to set it up properly. Maybe someday. I always want to see how far I can go. The point is, when you see something that looks like it requires sophisticated intelligence, don't assume the intelligence is where you expect it to be. It might be somewhere you hadn't thought to look. In the pattern, not the particle. In the system, not the individual. In the interaction, not the actor. That's the lesson of the hive mind. And it's one of the most beautiful lessons I know. Thank you.